Okay, so here we have the section B of the worksheet for 2011-2012 Unit 3. Part 1, Question 1, Part 1, the internal energy, heat and ideal gas. The internal energy of a piece of copper is increased by heating. Explain what is meant in this context by internal energy and heating. Well, internal energy is made up of both your kinetic energy and your potential energy. So you've got your kinetic energy, you've got your Ke, and your potential energy. The kinetic energy is the temperature will be increasing. And your potential energy, this is your bond energy. There's probably going to be some expansion, and so the potential energy of the particles of the atoms will actually be increasing because those atoms will be getting further separated from each other. Now, as far as heating is concerned, this is a transfer of energy to the copper. The copper is gaining in energy, so this is caused by the heating. This is a non-mechanical heating. Okay, then looking at question 2, the piece of copper has a mass of 0.25 kilograms. The increase in internal energy of the copper is 1.2 times 10 to the 3 joules, and its increase in temperature is 20 Kelvin. Estimate the specific heat capacity of the copper. Now we're assuming that most of the increase here is in the kinetic energy area, because although we will get some expansions in the volume, this will be very slight. Most of it will be in the kinetic energy, and so we'll have our Q is equal to MC change in temperature. The Q is, we are told, is 1.2 times 10 to the 3 joules. The mass is 0.25 C, and we get a change in temperature of 20. So we're going to multiply those out and we're going to divide. So we'll get 1.2 exponent 3 divided by brackets 0.25 times by 20, close brackets, enter. So it's about 240 joules per kilogram per Kelvin. Now here we can see that we've got two significant figures, and here this is fine, this is two significant figures, so that's all okay. Good. Alright, so let's keep on going. We're going to go down to the next question. Sorry, I have to close that down. Let's go here. Let's talk about this now. It says an ideal gas is kept in a cylinder by a piston that is free to move. The gas is heated such that its internal energy increases and the pressure remains constant. Use a molecular model of the ideal gas to explain the increase in internal energy and how the pressure remains constant. Okay, now to do this, I'm actually going to explain this. I'm going to make use of a simulation, one of our PhET simulations, which are so great. So we have a situation here where our pressure is constant. We're going to put some gas in here. Put some gas in there, and let's move you out a little bit like that. Let's move you out there, and let's make the pressure constant. And now what it said was that we are going to apply some heat. We're going to add some heat. Now we know when we add heat, we're probably going to have that the temperature is going to increase. So as I add heat, you can see the temperature increase. And what's happening here, because the pressure is constant, the volume has actually been increased. The piston, as you can say, is being moved out. Now why is this? Because because the temperatures increase, these particles are moving faster, and therefore by increasing the volume there are less interactions or less collisions taking place, and therefore the pressure is decreased by means of that. So the temperature leads to an increase in the velocity, which leads to an increase in the pressure, and so to keep the pressure constant, it must get bigger so that there are less collisions, and in this way you get a constant pressure. So let's go back here. So use molecular to explain the increase in the internal energy. Okay, so because you get the gases heated here, you're going to get an increase in the kinetic energy. Kinetic energy is going to increase, and therefore the internal energy will increase. Notice that we're talking about an ideal gas. In an ideal gas, we assume that all the energy, all the internal energy, is just purely made up of kinetic energy. We ignore all the potential energy effects within the gas because they are seen to be negligible. How the pressure remains constant? Well, as we saw there, the volume increases due to the increased velocity of the particles, of the atoms or molecules in the gas, and therefore to keep the pressure constant, the volume increases so that there are less collisions, something like that. Alright, good. So let's move on then to our next question, and we have this one over here. Okay, so define thermal energy, thermal capacity. So this is the energy required to increase the temperature of an object by 1 Kelvin. Outline what is meant by thermal equilibrium in this context, and let's just read through the question. We have a piece of copper is held in a flame and it reaches thermal equilibrium. The time it takes to reach thermal equilibrium will depend on the thermal capacity of the piece of copper. So the thermal equilibrium basically comes to a point where there is no net heat gain to the copper. Basically the temperature of the copper remains constant, and although it may be losing heat, it will also be gaining heat at the same rate. Good. So let's go down now to answer this question here, which is B. Okay, so the piece of copper is transferred quickly to a plastic cup containing water. The thermal capacity of the cup is negligible, so I'm not going to worry about the cup itself. The following data is available. So we've got the mass of the copper, the mass of the water, the rise in temperature of the water, the final temperature of the copper, the specific heat capacity of the copper, and the specific heat capacity of the water. So we have all of that. And let's just check and see back here. Sorry, let me just check something back at the top here. We are told that the copper is held on a flame, it reaches thermal, and we want to use this data to calculate the temperature of the flame. Okay, so basically what we need to calculate is the change in temperature in the copper, because once we do that, we'll be able to work out from the final temperature what the original temperature was, because the original temperature of the copper, because it was in thermal equilibrium with the flame, would have been the same temperature as the flame. Okay, so we have the heat lost, the Q lost by the copper will equal the Q gain, the heat gain, by the H2O. So let's put that in. We've got the mass of the copper is 0.12. We've got the specific heat capacity of the copper is 390 times the change in temperature of the copper, and the heat gain from the water, the mass of the water is 0.45 kilograms. The specific heat capacity of the water is 4,200, and the change in temperature of the water rise was 30. So from that we can easily calculate the change in temperature. So let's just do that quick. So we got 0.45 times by 4,200 times by 30, that equals, and we're going to divide that by brackets 0.12 times by 390 close brackets, and I get a value of 1211.5 Kelvin. We're going to get our change in temperature. So therefore the temperature of the flame would equal this 308 plus this change in temperature over here. So my final temperature, I'm going to put my answer in two significant figures here, because that's the least accurate that I've got. So I've got 1211 plus 308, and I get that, and I'm going to put it in two significant figures. So it's going to be about 1,500 degrees Celsius. Alright, so explain whether the temperature of the flame is likely to be greater or less. Well, it's likely actually to be greater, because we are assuming that all this energy that came from the copper, that it went into the water. But in actual fact, you would get a certain energy loss. There would be a certain heat loss here. So therefore the copper would have more energy, and therefore the temperature of the flame would likely to be more. Okay, I'm sure you can write that in for us. That would be great.